Hey, welcome back. Today we're diving into something that's kind of like an invisible science, but it shapes our entire world. From the phone in your pocket to the tallest skyscraper, pretty much everything we build. It all starts with this one fundamental practice, surveying. It's the art of measuring our planet with incredible precision.
So it really all comes down to this one big question, right? How do we take a design that's on a computer screen and actually build it in the real world? And not just build it, but build it with millimeter accuracy. And yeah, you guessed it. The answer is surveying.
At its heart, that's the whole game. It's figuring out exactly where things are in 3D space. But that simple idea, it's literally the foundation for every single bridge, tunnel, and building on this planet. It's that absolutely critical first step in turning an idea into a real physical place.
All right, so let's break it down. Let's start with the very first problem every single surveyor has to solve. Before you can build up, you got to map things out. And that means getting two things right: accurately measuring distance and setting a consistent direction.
And the first tool in the toolbox for that is scale. It's just a simple ratio, but it's what lets us take a massive, sprawling landscape and shrink it down onto a single piece of paper. Think about it. Without scale, a map is really just a drawing. With scale, it becomes a precise model of the real world.
Okay, but this is where it gets really cool. See, in the real world, nothing's ever perfect. No measurement is truly exact. Even something as basic as a tape measure is going to have some errors. So it's not a matter of if you'll have errors, it's what are they and how the heck do you fix them?
And this is just wild to me. You can see here that real-world physics actually messes with your measurements. Take a steel tape measure. On a hot day, it literally gets longer. If you don't pull it tight enough, it sags in the middle. Even the slope of the ground throws things off. Every single one of these tiny effects creates an error that surveyors have to calculate and correct for to get things right.
Okay, so you've got your distance down. Now you need direction. And surveyors basically have two main ways of doing this. You've got the whole circle bearing, which is just what it sounds like, a full 360-degree circle starting from north, just like a regular compass. Then you have quadrantal bearing, which divides that circle into four 90-degree chunks. It's all about making sure everyone is speaking the same language when it comes to direction.
But of course, there's another catch. What happens when your compass is straight up lying to you? If you're near a big metal deposit or even just a power line, it can create something called local attraction. Basically, magnetic interference that throws your reading way off. So how do you work with a tool you can't always trust?
Well, they've got some really smart, systematic ways to deal with it. So what a surveyor does is they measure a whole series of connected lines that are supposed to form a closed loop. They call this a traverse. Now, if everything was perfect, they'd end up exactly where they started. But when they don't, that little gap is called the closing error. And a method like the Bowditch rule is a genius way to spread that error out evenly across all their measurements, basically balancing everything out until it fits perfectly. All right, so we've got the flat 2D world figured out. Problem is, our world isn't flat. So now we have to tackle the third dimension, the challenge of mapping elevation. All the hills, valleys, and mountains that make up the actual terrain. Now this is a mind-bending concept. Think about this. If you're looking through a surveying scope over a really long distance, that straight line of sight is actually pointing a tiny bit up into space because the Earth is literally curving away underneath it. And to make it even crazier, the light itself actually bends as it travels through the air. So surveyors have to correct for both of those things at the same time.
So the big question is, how do you cram a 3D world onto a flat piece of paper? The answer is just brilliant in its simplicity, the contour line. It's just an imaginary line that connects all the points that are at the exact same height. It's like tracing the shape of the land at different levels.
And this is what makes contour maps so powerful. Just by seeing how close or far apart these lines are, you can immediately see the shape of the land. If the lines are all bunched up together, you're looking at a steep hill or even a cliff. If they're spread way out, you know the land is pretty flat. It's a visual code that perfectly describes the landscape.
Okay, so we've got distance, direction, and height covered. But what if you need to measure something you can't physically get to? Like how wide is a river you can't cross, or how tall is a building you can't climb? That brings us to our third major problem: how to measure things from a distance. This is where the tacheometer comes in, and it is a seriously clever piece of gear. It's pretty much a high-powered telescope, but it's got these special crosshairs inside. By looking at a measuring rod way off in the distance, the surveyor can see how much of that rod fits between the crosshairs, and from that, they can figure out exactly how far away it is.
And here's the magic. With just one look, one single observation, the tacheometer uses some pretty basic trigonometry to figure out both the horizontal distance and the vertical height. It completely turns what looks like a huge physical problem into a really simple and elegant math problem.
And you know, these ideas aren't just for measuring things that are standing still. They're absolutely crucial for things that move, like us in our cars on a highway. To build a smooth, safe curve in a road or a railway, you need to calculate it perfectly. It's surveying that gives us the math to plot out those perfect, swooping arcs on the ground.
Okay, we've gone from flat maps to 3D landscapes. It's time for the final, biggest leap of all. How do you pinpoint any spot, anywhere on the entire planet in an instant? Well, the answer, as you probably know, is flying right over our heads at this very moment. The Global Positioning System, or GPS, basically took all those core ideas of surveying and just blew them up to a global scale.
And this is a mind-bogglingly huge operation. The whole system depends on this web of at least 24 satellites, constantly zipping around the Earth, each one carrying an atomic clock that is just unbelievably precise.
So the whole thing works in three main parts. You've got the space segment, that's the satellites themselves. Then there's the control segment, which is a bunch of stations on the ground that keep track of the satellites and make sure they're accurate. And the user segment, well, that's you. That's the GPS chip right there in your phone.
So how does this all come together? Basically, your phone listens for signals from these satellites and measures how long it took for the signal to get to you. But to figure out your exact 3D position, your latitude, longitude, and your altitude, it needs to hear from at least 4 of them. It's a process called triangulation, and it's happening all day, every day, in space, just to tell you where you are.
So when you step back and look at the big picture, it's just an incredible story, right? From the ancient Egyptians using knotted ropes to today's satellites with atomic clocks, the basic goal has always been the same: to bring order to our world by measuring it. The only thing that's really changed is the tools we use to do it.
And that kind of leaves us with one last, really exciting question. We now have the power to measure and build our world with a precision that would have been unimaginable just a generation ago. The only real limit, at this point, is our own imagination. So, what comes next? What are we going to build with this power? Thanks for tuning in.